Hello students, today we have assignment 7.4. Three questions we have in this assignment. First one is define series resonance for series LCR AC circuit. Obtain expression for angular resonance frequency omega 0 and resonance frequency f0. Next question is draw resonance curve for series LCR AC circuit. Explain half power bandwidth and Q factor. Also obtain expression for Q factor. And lastly, a small topic, what is tank circuit, why it is called so. So mainly we will be talking about resonance in AC circuit when inductor, capacitor and resistor are connected in series. So let us start. We know that when we have resistor, inductor and capacitor connected in series with some source of alternating voltage. Voltage can be expressed as Vm sin omega t or Vm cos omega t, where Vm is maximum value of voltage. Similarly, current can be given as Im cos omega t minus delta. What is Im? Im is Vm by mod Z. Okay, and we know that in this circuit Z is R plus J omega L minus 1 by omega C, XL minus XC also we may say, and tangent of the phase of impedance is omega L minus 1 by omega C upon R. Moreover, we have two more equations. We know that Vrms can be given as maximum voltage by root 2 and IRMS can be given as Im by root 2. For this circuit, equation of power can be given as P is equal to Vrms IRMS cos delta, where cos delta is power factor and cos delta can be given as R by mod Z. So we'll keep all these equations in mind during this topic. Now we know that in this circuit the current IRMS actually depends on all the four parameters. IRMS can be written as Vrms by mod Z. Okay, and what is mod Z? Mod Z is under root of R square plus omega L minus 1 by omega C whole square. It means that if you want to change IRMS, apart from the source, the options which you have available are resistor value, inductor value, capacitor value and omega. So if you don't change component, that is R, L and C, still if you change omega value, angular frequency of the source, then also IRMS can be changed. And if you plot graph of IRMS versus omega, the graph comes out to be something like this. Omega I am taking on horizontal axis, IRMS on vertical axis, and it is observed that the graph is like this. So for some particular value of omega, let it be omega is equal to omega 0, the RMS current is found to be reaching its maximum value. It is called IRMS max. And when it happens, it is said to be in resonance condition. Now, why IRMS increases? Look at the nature of this graph. IRMS is increasing, reaching some maximum value, and then it decreases. So this phenomena uh, where IRMS achieves its maximum value is called series resonance. Series resonance is a phenomena in which current passing through AC circuit becomes maximum. Now, when the current becomes maximum, from equation 9, we realize that if omega L becomes equal to 1 by omega C, then then Z of the circuit will be simply R, and then IRMS will be VRMS by R only. This is maximum value of IRMS, and hence this equation is written as IRMS max is equal to Vm by R. Let it be equation 10. So, if we are asked what is series resonance, the answer should be that in case of series LCR AC circuit, if inductive reactance becomes equal to capacitive reactance, the impedance of the circuit becomes minimum, which is equal to R, and as a result, current passing through the circuit becomes maximum. This phenomena is called series resonance. And at that time, how much is the current passing through the circuit? The answer is it is Vm by R. Okay? And the frequency at which this happens, that angular frequency is called resonance angular frequency. And then if I compare omega 0 with 2 pi f0, then I can say that this f0 is resonance frequency. So how do we derive expression for resonance frequency? So we know that at resonance, angular frequency is denoted by omega 0 and omega L is equal to 1 by omega 0 C, and hence I can say that omega 0 square is 1 by LC, and so omega 0 is 1 by root LC, and let it be equation 11. This is the expression for angular resonance frequency. And here, if you take 2 pi f0 instead of omega 0, you can arrive at this. F0 is 1 by 2 pi root LC. Let it be 12th equation. So, omega 0, equation 11 and 12 are expression for resonance angular frequency and resonance frequencies respectively. Now, what if I change R value? Suppose you change R value of the circuit in equation 10. If we change resistor value, what will happen? Okay, let us have a look at it. If you change R value, then you will see that the resonance curve is changed. And what is the change in the resonance curve? If earlier curve is like this, for new R value, curve becomes like this. So you can say that sharpness of the curve changes if you change R value. Okay, let the values be R1 and R2. Okay, angular frequency or resonance frequency will not change. So when you change resistor value, if earlier this is the IRMS max for R2, the new IRMS max is more. It means that R1 is less than R2. Okay, and that is the effect of a resistor on IRMS max. But apart from that, if we consider power in this circuit, we know that power can be expressed as power is I square R. Okay, and hence power is directly proportional to I square. So maximum power is, sorry, so I can say that maximum power is proportional to IRMS maximum value. Okay, and don't forget that IRMS max. What is IRMS max? IRMS max, maximum value of IRMS. When you are considering, you are talking about resonance, and at that time you have only R. Okay, so don't forget it. It is our previous equation. I have not given it any number. This is the equation. Let us label it as 13th, equation 13. Now, in this graph, if I am getting maximum power for this value of current, there should be some other value of current for which power becomes half. So, as the power is proportional to I RMS max square, I can say that for half power, the value must be I RMS max by 2. It means that when power becomes half, the current must be I RMS max by root 2 if I take 2 inside the bracket. So this is the maximum current value, and then somewhere here I can say that I must have I RMS max by root 2. It means that if I consider vertical lines, I realize that there are two values of omega. Let the values be omega 1 and omega 2. So when the source is having angular frequency omega 1, current in this circuit is this much, IRMS max by root 2, and same is the current when angular frequency is omega 2. So within this range of omega, so I can say that if angular frequency is more than omega 1 and less than omega 2, power in the circuit is more than half and less than maximum power. Okay, when we have maximum power is when current is maximum, IRMS is maximum. Okay, and when you have half power, when do we get half power? Half power is when IRMS assumes value root 2 times less than its maximum value. And hence, this range of frequency is called half power bandwidth. What do you mean by half power bandwidth? Half power bandwidth, half power bandwidth is the range of frequency for which power in the circuit is half or more than half. So that is half power bandwidth. And one more thing we realize from this graph is that as you change R value, sharpness of the curve changes. And to express sharpness of the curve, a factor, quality factor is defined. So there are different ways of defining quality factor. We'll define it with omega value. So quality factor is defined as omega 0 by delta omega. You may also say it is f0 by delta f. What is omega 0? Resonance frequency, that is the frequency at which, angular frequency at which IRMS becomes maximum. And what is delta omega? Delta omega is the difference of omega 2 and omega 1, half power bandwidth, you must say. Okay, and now this is from definition. This equation is from definition of quality factor. You can also arrive at expression of quality factor in terms of R, L, and C. Let us see how to derive expression of quality factor with in terms of R, L, and C. And for that, we will need one of our previous equations. Let me note it down. Again, the equation which we need is omega 0 is equal to 1 by root LC, which is our 11th equation. So these two equations will need to derive expression for quality factor in terms of R, L, and C. What is quality factor? It is a parameter which indicates sharpness of the curve. If quality factor is more, sharpness will be more. And that can be understood from this equation also. If delta omega is less, Q is more. What do you mean by less delta omega? Less delta omega means that these values are close by. Omega 1 and omega 2 are close by. Then the curve will be sharp. So this is essential in so many electronic circuit. Wherever we are using uh, wireless devices like mobile or radio or TV set, there we need to tune our radio set or TV set or mobile handset with the external frequency coming. And it is tuned when we arrive at resonance condition. So for better performance, quality factor of the circuit should be very high. And let us see how to derive expression of quality factor in terms of R, L, and C. So we know that the current in the circuit can be given as I RMS is equal to VRMS by under root R square plus omega L minus 1 by omega C whole square. Now if I am talking about half power, then I know that current has to be, for power to be half, current has to be IRMS by root 2, actually IRMS max by root 2. Okay, and at that time the frequency uh, is either omega 1 or omega 2. Look at the figure once again. If I want power to be half, current should be IRMS maximum by root 2, and for that the angular frequency can either be omega 1 or omega 2. For now I am considering the frequency to be omega 2. So I will write this equation as under root R square plus omega 2L minus 1 by omega 2C whole square. Okay, and we also know that IRMS max is VRMS by R. So I can write this equation as VRMS by root 2 and R. That is equal to VRMS upon under root R square plus omega 2L minus 1 by omega 2 C whole square. So on simplification, you will get that 2 R square, okay, let me avoid skipping steps. So root 2R is equal to under root R square plus omega 2L minus 1 by omega 2C whole square. Taking square on both sides, we get 2R square is equal to R square plus omega 2L minus 1 by omega 2C whole square. Okay, and hence R square, taking this R on left side, we have 2R square minus R square, that is 1R square is equal to omega 2L minus 1 by omega 2C whole square. Again, to remove square on both sides, we take square root. So R is equal to omega 2L minus 1 by omega 2C. So far we have 14 equations. So let me label it as 15th one. Now we know that half power bandwidth is omega 2 minus omega 1 is equal to omega 0. This is sorry is equal to delta omega, and then I can say that if in the resonance curve, if I say that for this resonance curve, this is omega 0, let this be omega 1 and omega 2, and if this gap is regarded as delta omega, I should be able to say that this gap is delta omega by 2. Okay, so in terms of omega 0, if I express, I should be able to write this equation of omega 2 as omega 0 plus delta omega by 2. Look at this graph. If you want to arrive at omega 2, you can say that add this much in omega 0. So I can say that omega 2 is omega 0 plus delta omega by 2. So in terms of omega 0, I can write omega 2, and I am using this, let it be 16, in equation 15 I am substituting, and then what I have, I can write R as omega 0 plus delta omega by 2 L minus 1 by omega 0 plus delta omega by 2 into C. So omega 0, if I take common, I'll have 1 plus delta omega by 2 omega 0 minus 1 upon omega 0 C 1 plus delta omega by 2 omega 0. Now taking this in let me use the expression for omega 0. We know that omega 0 square is 1 by LC, or I can say that during resonance omega 0 L is 1 by omega 0 C. So instead of this 1 by omega 0 C, I can write omega 0 L in numerator, and then the equation of R can be written as omega 0 L 1 plus delta omega by 2 omega 0 minus omega 0 L upon 1 plus delta omega by 2 omega 0, which can also be written as omega 0 L 1 plus delta omega by 2 omega 0 minus 1 plus delta omega by 2 omega 0 raised to minus 1. See, two changes I have made. I have taken this omega 0 L out, and instead of writing this in denominator, I am writing with minus 1 power in numerator. Now if I apply binomial theorem and if I neglect higher order terms, the second bracket can be written as 1 plus delta omega by 2 omega 0 minus 1 minus delta omega by 2 omega 0. What I have done? I applied binomial theorem to second term and neglected higher order terms. So on simplifying, when you open the bracket, this one and this one will be cancelled out, and this minus sign and minus sign will make it positive, which when added to the previous term, you will have R is equal to omega 0 L bracket delta omega by omega 0, and that means that delta omega is nothing but R by L, and this is our 17th equation. Don't forget that earlier we have this equation. We already have mentioned that omega 0 is 11th equation, and so omega square, let this be 11th equation. So now if I define quality factor is nothing but omega 0 by delta omega. What is omega 0? 1 by root LC. What is delta omega? R by L. So rearranging the terms, I get L by R 1 by, 1 by root LC. And on simplification, you will get Q to be 1 by R under root L by C. This is the expression for quality factor of LCR circuit, and it is applicable for resonance condition. What is resonance condition? Resonance condition is when IRMS of the circuit becomes maximum. When IRMS becomes maximum? When impedance becomes minimum. When impedance becomes minimum? Impedance becomes minimum when this condition is satisfied, when inductive reactance and capacitive reactance becomes equal. At that time Z becomes minimum, IRMS becomes maximum, and that is resonance condition. And at that time we can define quality factor, which is a parameter which decides sharpness of the curve. Two equations for quality factor. This is one, and the other one is, by its definition, which can be given as omega 0 by delta omega. So that is all about series LCR resonance. Then we have one small topic, tank circuit. What is tank circuit? Tank circuit is this circuit. It is parallel combination of capacitor and inductor. So what is tank circuit? The circuit in which charged capacitor is connected with an inductor is called tank circuit. Why it is called tank circuit? Because we know that for capacitor the energy can be given as half Q square by C. Now in this circuit there is no way this energy can escape. For inductor the energy is stored in form of magnetic field. So when you connect inductor and capacitor in this fashion parallel to each other, they keep on exchanging charge and energy, and hence the total energy of the circuit remains constant. So you can say that this circuit stores energy, and that is why this circuit is called tank circuit. So that is all about assignment 7.4. Thank you.